Why do things change in the direction they do? This blob of ink spreads spontaneously through the beaker of water, and we should be very surprised indeed if the bits of ink gather themselves together again into the original blob. But why should we be so surprised? Why do things mix and never unmix? Fuels burn and never unburn. Weights fall to the ground and never spontaneously rise up again. In short, what are the rules which govern the direction of change? With mechanical things, weights falling to the ground and so forth, a useful rule is that they fall to a position of lowest energy. But this can't be a general rule because there are lots of changes which occur with no change in energy at all. In the mixing of liquids and gases, for example, energy changes are often zero or very small. This bromine, this orange gas, will spontaneously mix with air when they're put in contact. And what's more, these gases will never unmix in spite of the fact that bromine is a much heavier gas than air, and if it were purely interested in energy considerations, then the bromine would, of course, all be down in the lower part of the cylinder. So clearly, we're on the wrong tack in thinking about energy as an explanation of the direction of change. We need a new idea, a new concept. And that idea is the idea of disorder, chaos, randomness, mixed-upness, the idea of entropy. It's a familiar enough idea. From the early days of our lives in the nursery, we recognize a nice, tidy cube of bricks of this kind as an ordered arrangement, and we know that this is a rather unnatural arrangement in the nursery. There's a tendency for it to become chaotic. Spontaneously, it becomes random, and we call this arrangement disordered, at least this arrangement and this and this and this and all the other arrangements which are not the one which we started with, the nice tidy cube, we call disordered. And since there are more of these arrangements than the original cube, disorder is the natural state of things. As we become older and perhaps more sophisticated, we may play poker and bridge and meet order and probabilities in other ways. At a game of bridge, for example, we may be dealt 13 spades in one hand, but if we are, perhaps our natural reaction is to doubt the honesty of the dealer. Most of all, we're familiar with the fact that things tend to get mixed up. If I pour a red liquid into a colorless one, they mix. And if I pour back again, they don't unmix. And in fact, if they did, you'd think there was some jiggery-pokery on my part. Now, let's look into this in a little more detail by taking fewer molecules. Let me now take just two white molecules and two red ones, if you like, a white liquid and a red liquid. And if I shake these, they will probably mix. Shake them up in here, and they mix. They did mix. But I was gambling on that. I said they will probably mix. And what I meant was that there are 5 chances in 6 that they will mix. So I wasn't certain about it. Now, how did I know that it's a 1 in 6 chance that they won't mix? By counting all the possibilities which can occur. Now, I have those arranged on the board here. The balls are numbered, and there are 24 ways in which those 4 balls, those 4 numbers, can be arranged. And in this top left-hand corner, you see there are 4 of them which are the original arrangement, which was 2 white at the bottom and 2 red at the top. And the other 20 are what we call mixed. So there are 4 in 24, or 1 in 6, which are the original arrangement. And that's why the mixing occurs, because there are 5 mixed arrangements to 1 unmixed arrangement, and that's how I knew the probability. Now let me go one step further and take 100 balls. White layer again, and a red layer, and shake those. And these will mix. See? They mix as I shake, and now I could say these will mix. I was much more certain about it because the numbers are so great. In fact, the probability of mixing is so great that if all the people in the world who've ever lived shook a beaker like this all their lives, they'd be very bored, but also they would be very unsuccessful because they would never get the unmixing to occur. The probabilities increase so much because of the increase to 100 balls. And now, when we go to the million molecules which we have in this beaker of water, the probability of mixing becomes a certainty. As near a thing to a certainty as we shall ever meet in our lives. Well now, all these examples of disorder which I've been talking about have been concerned with the position of things, the disorder of position. And there's another kind of disorder which is equally important, and that is the disorder of motion. Let me show you what I mean by order and disorder of motion. These 6 pendulums I can set moving in an ordered way, but in only one way, which is ordered, that one. Now, alternatively, I can make each pendulum move in exactly the same way as before, but I can do this in a number of ways, random ways of motion of one pendulum with respect to another. There's one of them. Each pendulum is moving just as it did before, but there are many ways in which I can do this. There's a randomness about the motion. Not of position, but of motion. Randomness of motion is particularly important in the world of molecules, because the random motion of molecules is what we call heat. If I have a brick, I can set the molecules in that brick moving in 2 ways. I can throw the brick or I can heat it up. Here's a little brick, a model of a little brick in which we can see the atoms, and if I throw the brick, I do this. I make all the atoms move together in an ordered manner. But if I heat up the brick, I make the atoms move like this. The energy may be just the same as when I threw the brick, but it's certainly different. It's as different as a bump on the head and a burn from a hot brick. Now, the motion of molecules in gases is similar. It's a random motion which, if we could see it, would look something like this. There's chaos for you. It's almost a picture of chaos. And as I add more heat to the gas, I make the molecules move faster, increase their speed, I increase the randomness and the disorder and the chaos. And so we shall expect that there will be some relationship between the amount of heat we add to a substance and the increase in the disorder which results from adding that heat. If the idea of disorder is to be really useful to us, we need to be able to measure it. Let's begin by making disorder respectable and giving it a symbol. We'll call it P, and we'll define P as the number of different ways in which a distribution or arrangement can arise, and this can be a distribution of a position or of motion. And if all the ways are equally probable, then P will measure the total probability of that distribution. Now let's see how we count the number of ways. Here are a number of boxes, and I have 3 particles which I want to put into these boxes. What are the different arrangements, distributions, that I can have? Well, one distribution would be to put all 3 particles into this box. And there's only one way in which I can do that, 1, 2, 3. Another distribution would be to have 1 particle in each of these 3 boxes. But there are 6 ways in which I can do that, because the first particle can be put into any one of 3 boxes. Let's put it there. The second one into any one of 2. Let's put it there. And the third one just 1 way. So it's 3 times 2 times 1, 6 ways in which that can arise. And if I were dropping these things from a great height quite randomly, this distribution would arise 6 times more frequently than the one where all 3 balls are in the same beaker. There's just one other kind of distribution. That's the one with 2 in one beaker and 1 in another, and that distribution can arise in 3 ways. Now, in this case, there's no question of energy. All these boxes have the same energy. Let's now take it a step further and give them different energies. I've done that here by putting them on a sort of energy ladder. And this box has no energy. That has 1 unit, that has 2 units, that has 3 units. Suppose now, as an example, that the 3 balls have 3 units of energy between them. What are the possible arrangements? Well, one thing I can do, one arrangement, would be to give all 3 units of energy to one ball and put the other 2 down here. Another possibility would be to let each ball have 1 unit of energy, and then they would all go into the one box, like that. And there's only one other thing I can do, consistent with having 3 units of energy, and that is to have none, plus 1, plus 2 units of energy, 3 altogether. And we've already seen that this will be the most probable distribution because there are 6 ways in which that can arise. Identical with that, but this spread out arrangement can arise in 6 ways. Now let's go one step further. Suppose we have more. Suppose we have 30 particles and 50 units of energy. What then? What's the most probable distribution? Well, here it is. On this board, we have 30 particles, 50 units of energy, and this is the most probable distribution, consistent with those conditions. And you see, it's a sort of spread out distribution which tails off to the higher energies. And if we go to more particles and more units of energy, then we find that this tailing off follows an exponential or logarithmic law. It's called the Boltzmann distribution law. When Boltzmann first developed these ideas, it wasn't entirely clear what the physical meaning of these boxes of equal probability was. And it wasn't until the development of the quantum theory that it was realized that these are, in fact, the quantum states of the assembly of molecules. The development of the quantum theory also made it necessary to look a little more carefully into our methods of counting. But fortunately, it turns out, although these have to be modified somewhat, the results which we've obtained by the old classical methods of counting are, for most purposes, correct in most problems of physics and chemistry. Well, now that we know how to count the probability, the number of ways of one distribution, let's ask about 2 or more. The chance of my throwing, say, a 3 on a dice is 1 in 6. What's the chance of my throwing 2 3s with 2 dice? Well, it's 1 in 36. 1 over 6 times 1 over 6. Not 1 in 12, because probabilities multiply. They don't add, as many things such as mass and energy do. Now, most of us are more used to adding than multiplying, and we can overcome this little difficulty by using the property of logarithms. And instead of using p, using the logarithm of p. Because the total probability of 2 distributions is the product, if we take the logarithm of the product, we get log p1 plus log p2, and once more we can add these probabilities, or the logarithms of the probabilities anyway. So instead of using p, we use its logarithm. Now, for a reason which will become apparent in a minute, it's even more convenient to use not just log p, but log p multiplied by a constant, k, which is called the Boltzmann constant. So instead of using p as a measure of disorder, it's more usual and generally more useful to use k log p. Quantity k log p is given the symbol S and is called the entropy. And it's one of the most important quantities in the whole of science. The entropy can be calculated if we know p, which is the number of ways of arrangement. And p can be calculated if we know the structure of the substance. Now you can imagine that this is quite a complicated calculation unless the molecules are fairly simple, because there's a very large number of ways of arrangement. And fortunately, there is another way in which the entropy can be determined. And this depends on the fact, which we've already seen, that as we add heat to a substance, we increase the disorder, we increase p. So what we would like to do is calculate what this increase in p, and hence of entropy, is when heat is added to a substance. Now, you remember this distribution, which was for 30 molecules having 50 units of energy. Suppose I add just a little more heat energy to the substance, 2 units, shall we say, and allow nothing else to happen. It mustn't expand, there must be no other changes, so that all the heat appears as energy in these boxes, and the positions of the boxes do not change. Now, in that case, I shall be able to calculate a new distribution for the 52 units of energy, and there will be more ways. And if I take the difference between the ways of arranging the 50 units and the 52 units, for the heat absorbed, I know the entropy change. Now, I won't run through the calculation, but I'll give you the general result because it's a very simple and very useful one. And the general result is that if a substance absorbs heat Q at a temperature T degrees absolute, and no other changes, no expansion occurs, the increase, represented by this symbol delta in the entropy, S, is equal to the heat absorbed, Q, divided by the temperature. So you see, this equation measures entropy in heat units per degree absolute. And it is, in fact, the first way in which the idea of entropy was developed. The idea of entropy was developed in terms of heat units, and now, even though we have entropy changes which don't involve heat at all, we still measure them in heat units. And the K, the Boltzmann constant, in our other equation ensures that whether we measure entropy from this equation or from the K log P equation, we shall get the same answer in the same heat units. Let's look at the entropy changes in a simple case, the melting of ice, from both points of view. When a lump of ice melts and becomes liquid water, it has to absorb heat to do so. It's latent heat of fusion. And therefore, its entropy change, Q over T, will be the latent heat of fusion divided by the melting point. Simple as that. And we can calculate it in that way. On the other hand, from the point of view of molecular structure and disorder, we know that ice is a crystalline solid with a regular arrangement of molecules in that crystal with very little freedom. Although the regular arrangement isn't seen in a normal lump of ice, we're familiar with it in the splendid symmetry of a snowflake. On the other hand, liquid water is a random jumble of molecules. And being so, has more ways of arrangement, a higher P, arrangement both of position and of motion. And therefore we shall expect the entropy of liquid water to be higher than that of the crystalline ice. And so we get the same answer both ways, qualitatively and in fact quantitatively if we carry through the calculations. Similarly, when liquid water becomes steam, the molecules in the steam have greater freedom, more disorder, higher entropy. And from a heat point of view again, if heat is added to the liquid water, which it has to be, then for the evaporation to take place, then there will be an entropy increase, this time the latent heat of evaporation divided by the boiling point. Entropy, then, is a measure of molecular disorder, and it can be determined either by calculation from the properties of the molecules themselves or by the measurement of heat changes. It's entropy which provides the key to the question which we asked at the beginning, the question of the direction of change. If we take everything into account, and by this I mean the surroundings as well as the system itself, for example, in the connection of ice and water, we have to remember that the surroundings lose heat to the ice. If we take all this into account, everything is taken into account, then in any spontaneous change, the total disorder, the total probability, the total entropy always increases. This is the statement known as the second law of thermodynamics, the law of disorder. And no laws are more precise or more reliable than those of perfect molecular chaos.